Hello everyone, I'm Ethan Zhang and I am a PhD student at the University of Michigan. Today I am presenting our work, V2XSim, a V2X simulator for connected and automated vehicle environment simulation. Connected and automated vehicle technology is envisioned to bring lots of opportunities, including higher sustainability, mobility, and safety levels in transportation systems. However, corresponding research is still in its early stage, partially due to the lack of controlled testing facilities. Building real-world testbeds can be really costly, and they can have many restrictions. One solution to this problem is to build connected and automated vehicle environment simulators. That is what our work focuses on. In general, there are two types of simulators. The first one is hardware-in-loop simulator. This type of simulators combine hardware and software together to simulate a certain scenario. That helps capture the real-world performance of a certain kind of sensors or other parts. The second type is full simulation, which builds the simulation environment fully with software. It has two advantages. First, it's easier to deploy and to use compared to hardware-in-loop simulation, and secondly, it's less costly. Our work belongs to full simulation category. The proposed framework is built on top of the Gazebo engine, and Gazebo is a simulation engine that provides high-precision physics for robotics-related simulation. Existing work suffers from at least one of the following limitations. The first limitation is only focusing on a single vehicle. That is the main restrictions of most simulation related to this field. The second limitation is having no control performance guarantee due to the simulation platforms. For example, some work use game engines to simulate vehicles. Since the physics of game engines are mainly designed for gaming, their performance can deviate from real world a lot. Thirdly, shading vehicles has moving boxes rather than detailed robots. Last but not least, some simulators only provide 2D simulation. Our work, V2XSim, avoids all these forced limitations. The architecture of the proposed simulation framework consists of four main components, which are the vehicle's surrounding world, communication, closed-loop control, and APIs. The simulated world consists of multiple modules that represent the real-world environment. It's formed by two types of models, static models and dynamic models. Static models contain buildings, trees, and etc., while the dynamic models are vehicles. In the simulated environment, the simulator executes simulation commands. Vehicles interact with each other and with the whole environment, and then generate simulation results. Connectivity is a key feature of V2XSim. We develop a communication framework to simulate connectivity. In the communication framework, we focus on obtaining the message contents so as to enable users to analyze them and test the connectivity-related algorithms based on those messages. To successfully complete the communication process, first, each vehicle gathers and reports its own states in real time. To collect the relevant information, we built two extended modules on top of each vehicle model, which are the state listener and state publisher. These extended modules allow for monitoring each vehicle's model independently and can provide a standard message format similar to basic safety messages. After each vehicle obtains the relevant information using the state listener, its state publisher does not directly transit the BSNs to other vehicles. All messages are sent to a virtual RSU, which is an intermediate module layer that serves as a platform to filter messages before forwarding them to suitable destinations. This communication architecture design is inspired by the real-world Ann Arbor connected vehicle test environment. The virtual SEO provides a platform for users to monitor the entire system. It also reduces the likelihood of flooding messages compared to all units sending messages to a destination directly. In the architecture, we design a closed-loop control procedure to help users investigate the impact of vehicle control algorithms on vehicle motion. When a vehicle is given a control command, it executes that command, which leads to a state change. With the communication module in place, the updated state information is sent to the virtual SU and then through it to other vehicles. The control module of the vehicle obtains the messages containing information from other vehicles from the virtual SU. By decoding the message, the subject vehicle can obtain other vehicles' state information and use that updated state information to inform its own control algorithm. To simplify the control process and allow users to develop customized control rules, we provide a number of upper-level control APIs. Through these APIs, even without the full knowledge of Gazebo, users can still customize their own command using a limited number of predefined and common variables, which includes velocity, acceleration, and 6 degrees of freedom configuration, and etc. The control API is shown at the left bottom in this figure. This simulator also allows loss extension by integrating Gazebo loss packages into the simulator. In realization, the entire simulation world is constructed with 3D models provided by the Gazebo model libraries. In the work, we simulate the vehicle surrounding world with trees, gas stations, apartments, schools, office buildings, and etc. Serial routes are formed between building blocks. The vehicle model used in the simulator is a Paris 3D model with sensors, which is an enhanced Paris 3D model equipped with sensors such as cameras, LiDAR, and etc. In the figure shown here, the blue lines represent the LiDAR beams generated by the vehicle's onboard LiDAR. For lower-level modules, in general, we attach a Gazebo plugin to each vehicle model in order to implement closed-loop control, and in each plugin, we set a GZ message subscriber and publisher object pair to receive control command. All vehicle status are collected by the centralized virtual SEO and sent to other vehicles in each simulation update, based on the framework mentioned previously. To test the simulator and give an example, we implement the intelligent driver model for vehicle control in a V2X environment. We adopt the intelligent driver model proposed by Casting in 2010 by setting the minimum distance to 5 meters and desired speed as 12 meters per second. We assume the design speed for a following vehicle is the same as its leading vehicle's speed. The speed and acceleration changes during the simulation are shown at the bottom, as we can see from the results. Without any human intervention, the intelligent driver model algorithm is successfully implemented with this simulator and tested through the connectivity provided by the proposed simulator. There are certainly many other research areas that can be investigated using the proposed simulator, such as trajectory planning and etc. Here we provide a video demo to show the V2XSim. The simulator is built on Ubuntu and can only be launched with terminal command now. After executing the command, a simulation console will prompt out and start the simulation. In the demo, 4 connected vehicles are simulated. The blue lines are LiDAR beams generated by vehicle models. The messages collected by V2XSim are shown in the terminal window. And the demo can be found through the link given here. We also made this V2XSim open source. Now it can be accessed through GitHub with the link provided here. All source code can be found in the GitHub repository. We also provide a detailed user menu, as we show on the right, to indicate how to deploy, use, and customize the simulator. So in general, this work proposes a V2X platform, which is V2XSim for simulation of connected and automated vehicle environments. With the proposed platform, users can carry out detailed simulation of CAFs, including testing connected vehicles control algorithms. In the proposed simulation framework, every vehicle is constructed as an independent robot with multiple parts instead of moving boxes. The proposed simulator uses a virtual SU to establish communication between vehicles, which enables users to monitor the system status and enrich possible simulation scenarios. The simulator provides a platform to investigate connected and automated vehicle environments in a more cost-efficient way compared to real-world testbeds. And that's my presentation. Thank you very much for listening. Please feel free to ask me any questions.